So in this lecture we're going to talk about how you analyze stratified surveys. We're going to cover three things: why you stratify, and different kinds of stratification. So you can stratify by geographic region, you can stratify by survey, and you can stratify by some individual level thing like species or cluster size. And then finally we're going to talk about the limitations of distance in analyzing stratified surveys. So what you use stratification for, the two main reasons to stratify are you can reduce the variance and improve precision by stratifying, and maybe you're interested in density and abundance estimates in subsets of the region of interest or for subspecies or so on. So you can then, if you stratify, produce estimates at that sub-region or subspecies level. So the three ways you can stratify are by area or geographic region. So this is typically when density varies in space, you then divide space up into strata and do stratified estimation within each stratum. You can also stratify sort of less obviously by survey. So this is kind of stratifying in time. Usually you do, say, 2 surveys of the same place at different times, and then the first time you go is stratum number 1 and the second time you go is stratum number 2, even though both are covering exactly the same region. And the third kind is you can stratify by something associated with the individuals that you're surveying. And the two typical things are by species. So if you're doing a survey of more than one species, you might stratify by species. And the other typical way is stratifying by cluster size. Again, this tends to be in exactly the same geographic region. So we'll look at each of those kinds of stratification in turn. And the first and probably simplest one is geographic stratification. So in this simple example here, we have a survey region which is bounded by this dark line, and within it we have 3 strata. Stratum number 1 has an area A1, stratum number 2 has an area A2, and stratum 3 has an area A3, with the total area being the sum of those 3. Now the abundance in each region is the density in the region multiplied by the area. So in region number 1 we have a density D1 which we estimate, and our estimator is D hat 1. We estimate D hat 2 in region 2 and D hat 3 in region 3. The abundance estimate in the first region is the density estimate of the first region multiplied by the surface area of the first region, and the same for the other 2 regions. So the total abundance, just rewriting it because this turns out to be a useful way of writing the density, the abundance estimate for stratified surveys. The total abundance is just the sum of the individual abundance estimated, which is just the first area times first density estimate plus second area times second density estimate, and so on. And what about the density? Well, the total density is just the total abundance divided by the total area. Now we can write the total abundance as this thing over here, so that's on the top, and the total area we can write as the sum of the individual areas. And then we can factorize this a little bit, just calling the bottom thing capital A, and then it becomes a sum of the first density multiplied by A1 divided by capital A. First density multiplied by A1 divided by capital A. So that's the fraction, this thing in brackets here is the fraction of the whole area that is in stratum number 1, and we multiply that by the density of stratum number 1, and then the same for the other 2 strata in this example. And then we can write that briefly using the summation notation as the sum over stratum I equals 1 to 3, because we've got 3 strata, of this thing in brackets multiplied by the density. And the thing in brackets take note of, because what this expression here is a weighted sum of the individual density estimates, the stratum specific density estimates. And in this case, the weight, the thing in brackets, is a weight that's proportional to the surface area of the stratum in question. So we'll look at an example of geographic stratification. This is the scan survey of the North Sea and surrounding waters that happened in 2005. It was a survey of marine mammals. And you can see if we get the brown and blue areas, those are just different kinds of surveys were done in those areas. Let's just look at the blue bits, for example, or these purplish blue things. So we have a number of strata which are denoted with capital letters here. So this is stratum A, between that line and this boundary. Stratum B is the English Channel here. Stratum C, we can't see. Oh, there's stratum C there. D, E, F, and so on. So this is very clear geographic stratification. And then within each of these strata, track lines were laid down for a line transect survey, and the zigzag lines here are the transect lines. So from each of the survey we have a number of lines specific to that stratum, and attached to those lines we'll have detections. What does that look like in distance? So this is what a distance data set would look like. This is not those scans data, this is just an example data set. And the key thing here is the region. So region is stratum in this case. And what's visible here is we have two regions are visible. We've got an ideal, something we've called an ideal habitat region, and then a marginal habitat region. The ideal habitat region is 85,000 square nautical miles. So this is the A1. And this is 600,000, so this is A2. In ideal habitat, we have at least, we can see two transects. There might be more that are just above off the page because we're not looking at the whole data set here. Transect number 12 and transect number 13. And transect number 12 was of length 1 nautical mile, transect number 13, 80 nautical miles long. Transect number 12, we saw nothing. Transect number 13, we had a number of detections. And then in the marginal habitat, we have transect number 14 and probably some others. So that's what the data looks like in distance. What about the analysis? Well, if we look at this model definition properties tab, we specify how the analysis is going to be done. Now, if you have group data, then there are three main parameters that you're estimating. You're estimating an encounter rate, so that's given by this N upon L, an expected group size, given by this ES thing, and an F0, so a PDF evaluated at the origin. And in this picture we have three strata. So this column is stratum number 1 with 1 subscript. This is stratum number 2, and this is stratum number 3. And you can see that each of these strata has its own F0, has its own ES, and its own N upon L. So for each of them, we're estimating detection function or probability density function equivalently at the stratum level, the mean group size at the stratum level, and the encounter rate at the stratum level. So we specify that by ticking these stratum columns here. So we're going to get density at the stratum level, and it will always give us the density at the global level. So that's at this level up here. It's going to give us the density at the stratum level as well. And by ticking for encounter rate, ticking under stratum, that says that we want an encounter rate, a separate encounter rate to be used for stratum 1, stratum 2, and stratum 3. By ticking detection function under the stratum column says we want a separate F0 for stratum 1, stratum 2, stratum 3. And by ticking cluster size, it says we want separate mean group size estimates in stratum 1, 2, and 3. And then note this, these two fields here. The first one says that the global density estimate is constructed by working out a mean of the stratum density estimates, and you weight that mean by a stratum area. So that's exactly what we saw in a formula a couple of slides ago. We do have other options though. It may be, for example, that we believe or would like to investigate a model in which the detection function is the same for all strata, but the encounter rates are different and perhaps the mean school sizes are different. So that's denoted by this little tree over here. It's saying that we're estimating an F0 for stratum number 1, 2, 3. So there's only one F0 to estimate. We are estimating 3 mean group sizes and 3 encounter rates. How do we tell distance to do that? Well, it's just a question of ticking the right column here. So we've got density global, density by stratum, and then encounter rate by stratum, 3 encounter rates there. Detection function not by stratum in the global column. So one detection function, one F0 estimate, and then again cluster size separately by stratum. How do we decide whether to pool or stratify the F0? So how would we decide whether to estimate 3 F0s or just one pooled F0? Well, we're going to look at an example in which we have only 2 strata. So this is the data set that we looked at part of previously. And we've done one analysis shown on the left here where we've pooled all the data. We have 88 observations. And when we fit a detection function, the red line, to the pooled observations, that's the blue histogram in this picture, that's the fit there. Or we can fit it separately to ideal habitat stratum and the marginal habitat stratum. And you can see we fitted 2 separate detection functions here. This one has a narrower shoulder than the one in the marginal habitat, which would say that you can see a bit further, you can see a bit better in the marginal habitat than you can in the ideal habitat. But are these 2 curves different enough that we should be estimating 2 separate F0s, or are they similar enough that we really should be pooling our data? So that question is just a model selection question, and we can answer that using Akaiki's information criteria as we've used for model selection before. So let's look at this table. The rows of the table are the log likelihood function attached to the pool data or each of the strata, and I'll come to this last column at the end. The number of parameters. So for the pool data, we're fitting one hazard rate function which has 2 parameters, and then for each of the strata, we're fitting a hazard rate function. So that's 2 parameters for stratum 1, 2 parameters for stratum 2, and 4 parameters in total. And then the ARC we just work out for the pool data being this column. We work out as usual, it's just minus twice that plus twice this, which turns out to be 364.9-ish. We can also get an ARC for stratum 1 by doing the same, minus twice that plus twice this, and that gives us this number, 149.4-ish. And similarly, in stratum 2, we can do that, and we get an ARC of 213.3. Now, how do we combine? What we want to do is we want to compare this ARC to these 2 ARCs. How do we do that? Well, if these 2 data sets are independent, and when we've stratified and are estimating the other parameters separately in each stratum, then the data that go into stratum 1 are completely independent of the data that go into stratum 2, and so the likelihood function is just a product of the stratum 1 likelihood and the stratum 2 likelihood. So the log likelihood is just the sum of these 2 numbers, because logs of products are give you sum of logs. So that's this number. Just add these 2 numbers up to get the likelihood. The number of parameters, well, obviously that's just adding the 2 numbers of parameters for each of the strata together. And then because of the independence, we can just add the ARCs as well, and so we get this ARC. And so our comparison then is between this single ARC here, which is this single ARC that's associated with a stratified estimation, both strata, against this number, which is the ARC from the pooled. And you can see that the stratified ARC is smaller by just over 2 than the pooled ARC. And so what that says is that by ARC we should prefer the stratified analysis, as in we should fit separate F0s for each stratum in this case. So that gives you a way of deciding whether to stratify F0 or not. Okay, let's look at other types of stratification. So that was geographic stratification. Now we're going to look at stratification by survey. So we've got the same survey region. We're not cutting it up into separate geographic strata, though we're just treating it as one stratum. But it turns out we surveyed it twice. So we went, survey 1 is the solid lines, and then at some other point we came back and we did survey number 2. So survey number 2 is stratum 2 and survey number 1 is stratum 1. How do we deal with that? Well, it turns out that you deal with it pretty much the same way as you did with areas, the only difference being that the weighting, so this term here, which previously was area I divided by total area, now we weight by line length I divided by total line length. And that's not a unique way of doing this, but that turns out to be a good way of doing this, getting an estimate of total density. The other way is you could weight, which would also give you unbiased estimates of total density. And as I've said, this is exactly the same formula as we had before, except we have a different weighting term. It depends on effort instead of area. How do we do that in distance? Well, in the same model definition properties, we tick at this, all of these things at the stratum level, because we're estimating all parameters at the stratum level. But the difference comes in this box over here. So again, we've got a mean, it's a weighted mean, but the weighting is now different. Previously, this weighting was by the area of the stratum. Now it's simply a weighting by effort in the stratum, and we also need to tick this strata or replicates thing, because that tells us that these two strata cover the same geographic area. And finally, stratification by species. So again, we have our same survey region. We've done one survey now along these dashed lines, but we have two kinds of animals. We've got the black dot animals and the large white dot animals. The abundance obviously is just, the abundance estimate is just the sum of the abundance estimates, and the density of animals is obviously just the density of species 1 plus the density of species 2. So this is a sum, but it's an unweighted sum. And so in the model definition properties, we're doing everything at the stratum level, and instead of having a mean here, we just have a sum. Okay, so that's how we do stratified estimation and stratified estimation in distance in particular. And we looked at complete stratification, so F0, encounter rate, and mean group size estimated separately for each stratum. And we looked at combining F0 across all strata and estimating the other two parameters separately. But there are obviously various other options, and one of those options is illustrated here, as we've got a total density estimate, 3 strata, and we can estimate the mean group size and encounter rates separately in each stratum. But stratum number 1 and stratum 2, we think that the detection function is probably the same, so we want to investigate a model in which we combine those two to estimate a single F0. But we think that in stratum number 3 we have a different detection function, maybe different kind of habitat. And so we want 2 detection function estimates, 2 F0 estimates, the first combining being for both stratum 1 and 2, and the second being only for stratum 3. Easy enough to draw the picture, but distance won't do that sort of thing. It won't do, this is called multi-level stratification. We're stratifying differently at different levels. When I say distance won't do that, I mean it won't do it automatically. You can do it, but you've got to do it in bits and combine the bits yourself. So you do the separate stratum estimates for all of the parameters. Then you combine these two strata and you estimate this F0, 1, 2 for those two. And then you've got to combine the estimates you get out of this branch and the estimates you get out of this branch. You've got to combine into a single density estimate, but you've got to be a bit careful in doing that, because the estimates in this of density in this stratum and density in this stratum, they share parameters in this thing. So they're not independent estimates. And you've got to take account of that lack of independence due to the fact that they have a common detection function estimated for them when you combine them. And that's not difficult to do. It's a bit tedious to do. Details are in the distance sampling book. Can do it, but you've got to be careful how you do it. Okay. What are the alternatives to stratification in distance? Well, you need to be a bit worried about stratification if, when you cut your survey region into strata, you find that some of the strata have small sample sizes. So perhaps you have plenty large enough sample size when you do it across the whole survey region, but when you cut the survey region into strata, you find that within some of those strata, your sample size is too small for reliable estimation. Well, then your one option is just to combine strata until you have adequate sample size in each of them. But another approach is to use multiple covariate distance sampling. And essentially what this does is it puts the stratum in as an explanatory variable rather than as cutting your data up into bits. And in particular for the detection function, you can put stratum in as an explanatory variable into the scale parameter of the detection function. So that's the sigma parameter. And stratum is just one of the things you can put. What multiple covariate distance sampling lets you do is it lets you put any covariate into that. But in the context of stratification, we can put stratum in. So you can then fit using this MCDS, the multiple covariate distance sampling analysis engine, to fit a detection function at multiple levels. So you can do stratum specific density estimates even if you don't have enough data to fit separate detection functions for each stratum. By putting stratum in as a covariate, it lets you borrow strength from the other strata, to get a detection function that is different between strata but uses information from all strata to obtain it. And the details of this will be covered in another lecture.